Let us start lecture 42, and the course is on phase diagrams in single component and binary systems. And today's topic, it will be the same topic what we have discussed in the last lecture, that is isomorphous phase diagram and how to calculate. In fact, in the last lecture we have started doing our operations, and there we have found the equations for solid solution as well as equation for liquid solutions, and then what that has been done from the equation of unmixed as well as unmixed solid as well as unmixed liquid. So, once we got that, we have to now find out equations for equilibrium conditions, that is partial molar Gibbs free energy of A and B in solid and liquid, these two phases. Now, if I check how we have done it, in fact, if you look at the basic equations what we have got, which is, and of course, this is isomorphous binary phase diagram, and there we are doing it for A and B, which are forming A and B two metals, ideal solution. Okay. And the formulations are basically G2 equal to G1 solid liquid plus delta G mix solid liquid, where Xa and Xb are the mole fractions that would lead to 1 mole of solution, and temperature we are doing it at different temperatures. That means, every time we are fixing the temperature and trying to see equilibrium condition for solid and liquid solution. P is kept constant, 1 atmosphere. Okay. So, that is the condition we are getting, and of course, the melting point is TMB and TMA, and TMB is greater than TMA. That is the condition we have chosen, and the diagram what we are choosing is basically, if this is my XB, so XB equal to 1, XB equal to 0, and of course, Xa equal to 1, Xa equal to 0, two extreme points. This is temperature, and phase diagram looks like this. This is TMB, this is TMA, melting points. This is liquid, this is solid, and this is solid plus liquid. Okay. And we are trying to do it at a temperature T, and temperature T, if I try to see schematic representation for G1 and G2, this is, you just look back the previous lecture, you will get those points. G naught B liquid, this is GB naught A solid, which is 0, this is GA naught liquid equal to 0, and this is GA naught solid, and this is G1 liquid, this is G1 solid, XB is this way, this is G2 solid, and this is G2 liquid, and we are trying to get common tangent here. This is GB bar liquid equal to GB bar solid, and this side is GA bar solid equal to GA bar liquid. Fine. And this composition is XB liquid, and this is XB solid. And we have gotten formulas for G1 and G2. So this is G1 solid would be equal to minus XA delta G naught M A, G2S equal to minus XA, and everything would be solid. Okay. Similarly, G1 liquid would be equal to XB liquid delta G naught M A B, G2 liquid would be equal to XB liquid plus RT XA liquid ln XA liquid plus XB liquid ln XB liquid. Okay, these four formulas we have derived. Okay, so if I try to look at this particular diagram, what we have drawn in the lecture 41, so that particular diagram can be shown here. Exactly same diagram, I have copied it from there. Okay, so the same conditions are to be done, and for equilibrium conditions, so we can get Ga bar solid should be equal to G2 solid plus XB solid, G2 solid, Ga bar liquid should be equal to, let me write it down, okay, for, so this should be equated, this should be equated, we will get one equation, this will give me one equation. The another one would be from Gb bar solid should be equal to and Gb liquid would be equal to okay. So these two, if we equate them, we would get another equation. So these two equation would allow me to find out these two compositions. Okay. So our entire effort would be to find out these four equations, 1, 2, 3 and 4. These four equations, let us find out. And for that, we will check this particular diagram, and let us look at, so for that, to find out Ga bar solid. Okay, first let us find out. So for that we will be needing formula, basic formula would be G2 would be equal to, S would be equal to minus XA solid delta G naught M A plus RT XA solid ln XA solid plus XB solid ln XB solid. Okay. So we have to find out delta G2 solid, delta XA solid. So then that would be minus delta G naught M A plus RT XAS, then we can find out like this, ln XAS plus 1. Now this can be written as d dxas, let me put it like this, this 1 minus XA solid ln 1 minus XA solid. Okay. Since XA solid plus XB solid equal to 1. Okay. Bracket close. So then it would become minus delta G naught M A plus RT ln XAS plus 1 minus ln 1 minus XAS minus 1. In fact, I can convert this into again XBS. Okay. So then finally I can write equal to, I am just putting a gap here, you would understand why I am putting a gap here, A plus RT ln XAS, so these two would get cancelled, minus ln XBS. Okay. So now if I multiply with XBS, so then it will be XBS, this is XBS, this is XBS. Okay. Now if I add up G2 solid, so G2 solid will be minus XA solid delta GMA plus RT XA solid ln XA solid plus XB solid ln XB solid. Okay. Now I see that this term and this term would get cancelled each other, would get cancelled. Now I'll be left with, would be equal to minus XAS plus XBS delta G naught M A plus RT XAS plus XBS ln XAS. So then GA prime solid should be equal to G2 solid plus XB solid, G2S dXAS would be equal to, this is 1 again, this is 1, so minus delta GMA, so this is equal to 1, this is equal to 1, plus RT ln XAS. So we can say G2S GAS equal to minus delta G naught M A plus RT ln XAS. Let's say this equation is 5. We have to find out for, let's say, let us find out GA bar liquid. So for that we will be needing liquid solution equation, that is G2L should be equal to XPL delta G naught B RT XA ln XA, all would be liquid, XPL ln XPL. And in this case, let me just tell you one thing, this G2 line, what we are doing, So, this G2 line is basic G2 line for liquid as well as solid. Any composition I can reflect that G2 line through this equation. For G2 solid, similarly I can get all those composition I can get for G2 solid. Now, to find out this, I have to, the way we have done it for G A bar solid, we will do it for G bar A bar liquid. So, then I can do it delta G2 liquid delta XA liquid should be equal to, this would be XP equal to 1 minus XA liquid plus XB liquid should be equal to 1. So, XB liquid I can write it as XA liquid. So, then if I try to do this for this one, so then it will be delta G naught M B. And remember, for a particular temperature, this quantity is a constant quantity, that is not variable at a particular temperature. So, this plus RT, it becomes, do it XAL plus 1 minus ln 1 minus XAL minus 1. I can do this way. Okay. Then I can multiply with XBL should be equal to minus XBL plus RT XBL ln XAL plus, and this 1 will get cancelled. So, minus XBL ln XBL. Fine. Now, we know that G A bar L should be equal to G2L plus XBL delta G2 dow Gx dxAL should be equal to minus XBL delta G naught MB plus RT XBL ln XBL XAL minus XBL ln XBL plus XBL delta G naught MB plus RT XAL ln XAL minus XBL ln XBL. So, this would cancel these two terms and we will be left it, and this would also this two term will cancel. So, now we can get GAL, and GAL bar is equal to RT XAL plus XBL ln XAL. So, we get GAL should be G bar AL should be equal to RT, this is 1. So, RT ln XAL. This is equation 6. Okay. So now we know as per equilibrium GAS equal to GA bar L. If we go back, you see this. Okay. So that's what we are doing here also. So then we can write equation 5 is this one. So minus delta G naught A okay. So then we can, this is equilibrium condition. Equilibrium condition at a particular temperature and pressure, that is chemical equilibrium. We can say also chemical equilibrium. Okay. Now we can put it like this. So you can put it like this, RT ln XAL divided by XAS should be equal to minus delta GM naught A, then XAL should be equal to XAS exponential minus okay. So this is another important equation. So this equation, let's say equation 7. So we get an equation for liquid solution with reference to A composition, with reference to A. Okay. So that's what XAL and XAS we are considering. So then we are getting one equation where R is the gas constant, T is the temperature of consideration, and delta G M0 A is nothing but the melting free energy change for A at that temperature. Now we will find out for two other partial quantities and equate them. We have to find out GB bar for solid should be equal to G2 solid plus XA solid delta G2 solid delta XB solid. Okay. And G2 equation, solid equation is minus XA solid delta G naught M A plus RT XA solid ln XA solid plus XB solid ln XB solid. So we get, if we do delta G2 solid delta XB solid would be equal to, and we know that XA solid plus XB solid equal to 1. So XB solid should be equal to 1 or XA solid should be equal to XB solid. So we can convert all the XAs in terms of B, and then we can find out this quantity. So we can do this that if I do that way, so then it would come delta G naught M A, it will come positive, plus RT, this would come negative ln XAS minus 1 plus ln XBS plus 1. So then we will multiply with XB. So then X, of course XAS is solid, XAS will multiply because we have to find out this. So then delta G dou G2S dou XBS would be equal to XAS delta G naught M A plus RT, because there should be a minus sign, minus XAS ln XAS plus XAS ln XBS. And now we see a B would be equal to, so XAS delta GMA plus RT minus XAS ln XAS plus XAS ln XBS. Of course, G2 is minus, so minus XAS delta G naught MA plus RT XAS ln XAS plus XBS ln XBS. Okay, so you see that this term, these two terms are cancelled. So now, and of course these two terms would also be cancelled. So then we'll see, so this and this two quantities, if we add them, it will lead to 1. So we have seen that G bar SB should be equal to XA solid plus XB solid ln XB solid. So this is equal to 1, then GB solid should be equal to, this is bar, partial quantity, there is an RT missing, so RT ln XBS, so it would be RT ln XBS. So let me see if I have missed any term in the previous calculations, the final terms. No, everything is fine. So here it's coming like this. So this is one equation, which is, let's say, equation, we have ended our equation with equation 7. So I can put this equation as equation 8. Now let us find out partial molar Gibbs free energy for B in liquid should be equal to G2L plus XAL. Okay, so we are trying to find out this and this. So G2, then we have to G2L. If I try to find out this quantity, so here G2 is G2L equal to XB delta G naught B plus RT XA, and this is liquid ln XA liquid plus XB liquid ln XB liquid. Okay, let me see if I have missed any terms here. For solid, everything is solid. For liquid, everything is liquid. Fine. So this would be then delta G naught MB plus RT minus ln XAL minus 1 plus ln XPL plus 1. So this would get cancelled. So now if I multiply with XAL, so this would be minus of XAL, and here also XAL, and this is also XAL. Okay, so I have multiplied that. G bar B of liquid should be equal to, this equation I will follow. So XAL plus RT minus XAL ln XAL plus XAL ln xbl. This is basically, this quantity is nothing but this one. Okay, this is this. So I will be adding G2. So then this would be xbl delta G naught mb plus RT xal ln xal plus xbl ln xbl. Okay. So I could see that these two quantities, they will cancel each other. So now we'll be left with GBL bar equal to XAL plus XBL delta G M naught plus RT XAL plus X. Okay, this quantity is basically for G2. So here it should be B. So XBL ln XBL. Okay. So this is equal to 1, this is equal to 1, G bar B of liquid equal to delta G naught M B plus RT ln XBL. So this is another equation, which is, let's say, equation 9. Now I will equate equation 9 for chemical equilibrium at T and P, GB bar solid equal to GB bar liquid. So then I can, so this is equation 8, this is equation 9. I can write RT ln XBS equal to delta G naught MB plus RT ln XBL. So I can write XBL ln XBL XBS would be equal to delta G naught MB divided by RT with a minus sign. So then I can get, or I can write XBL should be equal to XBS exponential minus delta GMB divided by RT. So we got one equation for this equation. If we recall equation 7, we got this, and equation, let's say this equation is equation 10. So now we got two equations, XAL equal to XAS exponential minus delta G naught MA divided by RT, which is equation 7, and XBL equal to XB solid exponential minus delta GMB by RT. This is equation 10. Once we get that, okay, we can get the equation for, in fact, if I go back to these two composition, this composition XBL, the liquid B composition, can be also expressed in terms of XAL. This can be also expressed in terms of XAS. Okay. So we got this and this, okay, in terms of XAS and XBS. So we got this. Now we have to solve that. Okay. So now let us find out from these two equations. So from 10, I can write this as 1 minus XAL, because XA L plus XBL should be 1, and XA solid plus XB solid should be 1. Okay. So that should be maintained. Okay. So then I can write 1 minus X, everything should be taken in terms of A. AS exponential minus delta G naught M B by RT. Okay, I can write this. So now in this I replace XAL with equation 7. So from this I can write 1 minus XAS exponential minus delta G naught MA divided by RT equal to exponential minus delta G naught MB by RT minus XAS exponential minus delta G MB naught RT. Okay, I can write that. Then from here XAS, I can put it like this, exponential minus delta G M naught MA RT minus exponential minus delta G naught M B divided by RT equal to 1 minus exponential minus delta G M B divided by RT. So XAS equal to 1 minus exponential minus delta G naught M B by RT divided by exponential minus delta G M A by RT minus exponential minus delta G naught M B divided by RT. Okay, so this is one expression for solid solution in terms of A. I can find out XAL. XAL equal to XAS exponential minus delta G naught M A divided by RT. So this is equation 7. So from here I can write XA equal to 1 minus exponential, I'll just replace XAS what we have found out here. Let's say this is 11. So 11, equation 11 is replaced in equation 7. So exponential minus delta G naught M B divided by RT. This is with exponential minus delta G naught M A divided by RT divided by exponential minus delta G naught M A divided by RT minus exponential minus delta G naught M B RT. Okay, so we got, this is let's say equation 12. So now you see this, if we solve, and for that what will be needed? Will be needed delta G naught M B would be equal to delta H naught M B Tm B minus T, the temperature where we are finding this, and here Tm B. Okay, and we need another which is delta G naught M A equal to delta H naught M A T M A minus T divided by T M A. So, all those formulas, if we put it in equation 11 and 12, we get solid solution composition as well as liquid solution composition in terms of A. We can also do it in terms of B. So, now if I come back to this particular figure, so we can actually, we have found out in terms of XAL, and we have found out in terms of XAS. So, we can also do it for XBL and XBS, and in order to do that you have to just operate with equation 7 and 10, where instead of operating with XAL and XAS, we do it with XBL as well as XBS. Okay. So, now you see this equation 11 and 12 and these two equations will give us the entire isomorphous phase diagram, starting from melting point of TB M to melting point T, the melting point of B to melting point of A. Of course, beyond melting point of A, these two lines will not intersect each other, because let us say beyond liquidus line, we will always find a situation that liquid free energy will be lower than the solid free energy, as well as below solidus line, solid free energy always would be below the liquid free energy. So, that is what below solidus everything would be solid, that is solid will be stable, and beyond liquidus everything would be liquid. Okay. So, that way we can find out, we can calculate isomorphous phase diagram. Of course, please understand that this is based on a simple ideal solution approach. In fact, if we do it for a real solution, we can get such equations and we can solve for solid solution composition and liquid solution composition at a temperature between two extreme melting points, two melting points of pure A and pure B, and then we can find out those compositions which are equilibrium at that temperature. Okay. So, let me stop here. So, we will solve some problems on this, okay, and then so that it will be clear to you. Okay. You can also try it at home, and you will see that nicely this will come. In fact, you can try it with nickel and copper. You can get those data, thermodynamic thermochemical data, which is a melting point of copper, melting point of nickel, as well as their enthalpy of melting, and you can find out the isomorphous. In fact, nickel and copper, that is a perfect example of isomorphous phase diagram. Okay. So, let me stop here. Thank you very much.